Hello, my name is Sánchez, and I'm going to talk about our work Quaternion monogenic layer resilient to large brightness changes in image classification. The agenda is as follows. As an introduction, we are going to discuss why to go beyond conventional CNNs. The mammalian visual system is invariant to many transformations such as large brightness variations. However, the current CNNs classifiers are not. Previous works indicates that learning of invariant response might fail even with large augmentations in the training process. In the figure, we present an example about how the CNN classification performance decreases when it is tested with different contrast variations. Our strategy stems from the high dimension of the representation of the images. For instance, many people recognize that the choice of representation has an enormous effect of performance of machine learning algorithms, as is presented in the next figure, transforming Cartesian coordinates to polar coordinates. But for an image, it is not easy to propose a polar transformation only using real numbers. As a result, we propose to use Quaternion to represent each pixel in 3 dimensions as a new representation. And in particular, we compute the local phase by using the monogenic signal. The Quaternion monogenic layer, called as M6, is based on the monogenic signal as a 2-dimensional extension of the analytic signal proposed by Michael Felsberg. The monogenic signal generates a quaternion with 3 elements from a real signal using the Riesz transform. It is important to remark that we use the Fourier space to implement the convolutions with a log arbor function and the Riesz kernel, H1 and H2. After these convolutions, we compute the local phase and the local orientation. In the next steps, we normalize and stack the phases in the HSV color space, and finally it is transformed to RGB color space. As a result, we obtain 6 channels as an output, where it is possible to encode the local features like lines, edges, and its orientations into different colors. As an example, we present a circle and its corresponding feature map, RGB phi, which stands for phase, and RGB theta for orientation. Data and experimental setup. For the dataset, we are using C14 and cats vs dogs, which are RGB color model and 8 bits. The equation 1 was used to simulate the brightness degradation levels in the dataset. B0 is alpha equals 0 and means no brightness changes. For B1, alpha is 0.3, B2 is alpha 0.4, and B3 is alpha 0.5 over the maximum grayscale value. The figure shows an example of degradation levels and their effects. We consider 3 basic architectures, defined as shallow CNN A1, medium depth CNN called A2, and a very deep called A3, which represents a ResNet 20. Each acts as a double architecture, one standard a convolutional network, and the other the M6 on the top. The experimental setup is organized as follows. Each model is trained with a specific degradation level and tested against all the degradation levels. For example, the model trained with B0 is tested with B0, B1, B2, and B3. Results. The results present accuracy and variance values of the classification in the test set according to our experimental setup. We remark in boldface the highest average and the lowest variance. The mean values of the accuracy of the same CNN architecture is lower in comparison with the architecture using M6. We notice the high stability of the M6 averages and the corresponding small values of the variance. For A2 models, we see the same behavior for both datasets. The results using ResNet 20 are consistent with the previous experiments. We emphasize that the boosted performance of the M6 under large brightness changes is coherent through the geometry of the feature representation. As a conclusion, we demonstrate that M6 classifies images in spite of large brightness changes. The experimental results are consistent with the geometrical observations that the local phase and the local orientations are invariant to variable brightness conditions. Among the possible scenarios to use M6, we count self-driving cars under haze conditions, surface glazes in medical images, or day-round autonomous video surveillance. Finally, the main references are the following.